In this series of lectures, we are going to talk about nuclear chemistry. And this is a topic that kind of is very different from what we've been doing in chemistry so far, which is focusing on how electrons interact with each other on different atoms and form bonds and molecules and how those can change in a chemical reaction. And now we're going to ignore the electrons in the atom and focus just on the nucleus, which is very different, and look at the changes in structure that occur at the nucleus. This topic, though, I find fascinating, and I think it's one that all of us have some level of intuition about just because it's something we're familiar with just by existing in our society. Like pop culture has given us an exposure to nuclear chemistry already. And that might be through the idea of nuclear reactors, like especially if you watched the Chernobyl series last year on HBO, or if you are familiar with radioactive tools for diagnostic or treatment in different types of disease states, primarily things like cancer or tumors, which is kind of an unfortunate exposure to this topic. Yeah. So we're gonna focus on these things, and they're fascinating. There's a lot of applications in our daily life. But let's start out with a lot of new definitions, and let's kind of set the stage for our conversation about nuclear chemistry. So, nuclear chemistry is the study of changes to the nuclear structure of the atom, and that nuclear structure of the atom is just the neutrons and the protons. And again, we've focused on electronic structure for a long time now, which is what are the electrons around the nucleus doing? And now we're going to focus in on what's actually happening in the nucleus. So if we remember our overall atomic structure from Chemistry 161, in chapter 2 of your textbook, if it feels rusty, we have an atom that is composed of an electron cloud that makes up the volume of the atom. And then the mass of the atom all comes from the nucleus, which is really tiny and in the center. And that nucleus is composed of protons and neutrons. And we call these nucleons. So it's kind of a new word for us. Nucleon refers to either a proton or a neutron. It's a way of saying a generic subatomic particle with mass. And in the scope of this class, we're going to keep our discussion of subatomic particles to electrons, protons, and neutrons, so we could dive a lot deeper in another class. And so if we have an atom with a certain number of neutrons and a certain number of protons, the number of protons is going to tell us what element it is. And we track that with the atomic number. So for carbon, the atomic number is 6, and that means we have 6 protons. And that's how we define carbon. Any atom with 6 protons is a carbon atom. The number of neutrons can vary, though, and the elements still be the same, and we call that different isotopes. And so when there's differences in the mass number, which is the protons plus the neutrons for an element, that means if there's variation in the neutrons, we're looking at different isotopes. And so an example of an isotope of carbon is carbon-12. It has 6 protons and it has 6 neutrons. A different isotope of carbon is carbon-14, which has 6 protons because it's carbon, and 14 minus 6, which equals 8 neutrons. And so we have a different number of neutrons, we have a different isotope. Now, if we had a sample that was only carbon-12, we would be looking at a pure sample of the same nuclide. So a nuclide is just a single type of nucleus, meaning one amount of neutrons and one amount of protons. A different nuclide of carbon would be carbon-14. So thinking about how the nucleus forms, we have protons and we have neutrons, and they come together and they're held together and they form a nucleus. And the force that holds that nucleus together is called the strong force. It's one of our 4 fundamental forces in the universe: strong, electromagnetic, weak, and gravity forces. And of these 4, which you will probably learn quite a bit more about in your physics class, we're focusing on the strong force. and we won't spend too much time on it, just to say that we've thought about attractive forces as electrostatic. I saw electromagnetic. So electrostatic attractions and forces are between positive and negative particles, and that's what holds an electron to the nucleus. It's what attracts atoms together to form bonds. It's what attracts molecules together to interact in a solution. And within the nucleus, we don't have positive and negative charges. There's no electrostatic attraction. And so the attraction that's holding it together is a strong force. And it's very, very strong over a short distance. And in that short distance where everything is in the nucleus, it's powerful and it holds it together. And the effect of that strong force is that when you bring these different subatomic particles, protons and neutrons, together into an extremely small space, and from an electrostatic perspective, you're like, well, but the positive charges should be repelling each other. But if you get them close enough and the strong force comes into effect, they'll actually stay together, and it'll stabilize those particles by being in that arrangement. And when that happens, it releases energy. And so some of the mass of these separate nucleons coming together, the protons and neutrons, is converted into energy as the nucleus forms. And now that difference is just going to be the mass difference between the mass of the nucleus and the mass of all the separate particles that make up that nucleus summed up together. We call that the mass defect. And it's a result of the stabilization of those particles by forming the nucleus by the strong force. And so we can figure out how much that energy is that's released as that nucleus forms. That signifies that it's forming a stable arrangement. And we're going to call it the binding energy. And now we've seen this word before. We've seen binding energy before when we talked about electronic structure of the atom. We talked about it in terms of the photoelectric effect in the context of that. And we were able to see that an electron held electrostatically to a nucleus can be removed. And the amount of energy that it takes, usually by shining light on the material, the amount of energy it takes that electron to be absorbed to then be removed from the mass is the binding energy of the electron. And it really is just how much energy is there holding those two together. And so the binding energy of the nucleons is really what is the energy holding those nucleons together as an effect of the strong force rather than the effect of an electrostatic attraction between an electron and the nucleus. But it's the same general principle. And so we can calculate that binding energy from our mass defect. And so we use this mass defect mass, which we'll calculate in atomic mass units, and we'll convert it into mega electron volts. Mega electron volts can then be converted into joules, and so we'll have a way of tracking energy. And just kind of a style, not stylistically, but the kind of norm in chemistry is to report this energy in mega electron volts rather than in joules. And we'll then take this information about binding energy and talk about how this predicts nuclear stability for a nucleus. And we see that the greater that binding energy, the more stable the nucleus is, the more strong force attractions that are holding it together. And so the more stable it actually is. So I'm going to walk through just a quick example problem of this and then give you an opportunity to try one. And one of the things that we're going to need for doing calculations around mass defect and binding energy are the mass of the subatomic particles. And in your lecture notes, you should have a page that has those written out for you. I'll put them here now. So the mass of a neutron is going to be equal to 1.00866 atomic mass units. And then the mass of the proton, we see some variation in what is reported. So it's going to depend a little bit on what textbook you use. In the OpenStax textbook, it reports it as 1.00727 atomic mass units. A lot of my example problems, though, were developed when I was teaching out the TRO textbook, and so I tend to use the version reported there, which is 1.00783 atomic mass units, and it doesn't matter which one you use. You'll get in the same ballpark. All right, so let's take a look at one of these. So we're going to talk about the mass defect in the nuclear binding energy for carbon-16, and we're given the mass of the isotopes, or the nuclides nucleus. And so the information that we need to use is the mass of the proton and the neutron, but we also need to determine how many of those particles we actually have. And so for carbon-16, and that 16 is the mass number. It's often written up here in the upper left-hand corner, but you'll also see it written as a dash following the element symbol as well. Well, we know that from the periodic table, carbon has an atomic mass, or atomic number of 6, which corresponds to the number of protons. So using this information, I know I have 6 protons and 16 minus 6 neutrons, which will be 10. And so I can use this information to calculate the sum of the mass of the particles, or the nucleons. And then if I subtract from that to the mass of the nucleus, I'll have the mass defect. So that mass defect is going to be equal to, I've got 6 protons, so I'll do 6 times the mass of my proton, which is 1.00783 atomic mass units, plus the 10 neutrons, so 10 times the mass of a neutron, which is 1.00866 atomic mass units. And from that, I'll subtract the mass of the nucleus, which is that 16.014701 atomic mass units. And so my mass defect is equal to 0.118879 atomic mass units. All right, so that's that difference in mass that occurs when we form the nucleus for carbon-16. But this is a mass unit, and I really need to be able to have this in terms of energy to think about the binding energy of the nucleus, or per nucleon. So I'm actually going to convert this into energy units. And it's a one-step conversion using the conversion factor that we have, 931.5 mega electron volts per 1 atomic mass unit. And when I calculate that, I get 110.74 mega electron volts. You could also convert this into joules from there as well. I'm going to keep it in mega electron volts because that's what we typically do in chemistry. And so this is that binding energy for the whole nucleus. But I've been asked to give it per nucleon, which is the difference between the two. It'll be smaller, right? It'll be per nucleon, but it allows us then to compare it to other nucleuses with different numbers of protons and neutrons. And we'll do that when we talk about stability. So I'm going to take that to calculate the binding energy. I'm going to take that 110.74 mega electron volts and divide it by the 16 nucleons that are in my nucleus. So that's the protons plus the neutrons. When I do that, I get a value that is 6.921 mega electron volts per nucleon. Now there's a practice problem following this. Give it a try on your own, and there'll be a solution in a video that follows.